Hello, friends, colleagues, C++ learners, students. Again, this is Dr. Satish Singhal, PhD, Professor of Computer Information Technology at Rose State College, Midwest City, Oklahoma. I'm back to do the C++ 11 Tutorial 2, Part 2. In Part 1, we showed how we gave the introduction to the C++ 11 tuples, and we discussed various tuple functions actually. In this part 2, we are going to show you how tuples are actually more useful than what we were able to show in the part 1 using functions that return tuple. Okay, and functions returning tuples become a very useful software technique. Okay, one big advantage of tuples is that ordinarily, unless pass by reference is used, functions can only return one value by return mechanism in C++. Okay, mechanism return one value, but you can add pass by reference to return additional values. But big advantage of tuples is that functions can return multiple arguments by return mechanism because they can return actually a tuple which has many parts to it, many data stored in it. And we do not have to use pass by reference to return values. Some of you might say, okay, what's wrong with pass by reference? Actually nothing, although some languages like Java claim that pass by reference is unsafe and it can create bugs in the software. So if you believe that, then certainly functions returning tuples will be a good idea. Okay, so we did a function to get roots of quadratic equation some time ago, and this function computes real roots of the quadratic equation. The function we did doesn't really compute the imaginary roots. And that function had this kind of prototype. Bool is the return type. GetRoots is the function name. It takes three coefficients of quadratic equation A, B, and C. A is the coefficient of x squared, B is the coefficient of x, and C is the coefficient of, C is the constant, not a coefficient of x. And then, so three constants of quadratic equations are taken as an argument. And then, by reference mechanism, two real roots are returned, root 1 and root 2. Okay? So function returns it true if roots are real and populates the values of parameters root 1 and root 2 with real root values. If roots are imaginary, then function returns false and root 1 and root 2 are not changed. And the link to this video is here. We'll also embed the link to that video below so that you can click it and watch it if you need to. But the problem with this function we just showed, which is on this video here, is the mixture of passing by value and reference and by return mechanism. Returning tuple as a return value from function solves this problem for us. We don't have to mix the two mechanisms. Okay, so getRoot function that's going to return a tuple, its prototype is below, the tuple word, data type, angular bracket. Still we have to return a bool. It'll be true if roots are real and be false if roots are imaginary. But then we have three double types. When roots are real, which means this is true, then there are two real roots and we'll populate them into these two third is the imaginary, we'll set that to 0. But if it is false, that means roots are imaginary. Then we'll have 2 real roots and 1 imaginary root, and we'll populate all 3 of them. Okay. And then A, B, C, as you know, are A is the coefficient of x squared, B is the coefficient of x, and C is the constant for the quadratic equation. Okay. So we show the whole thing in Xcode. So we'll go to Xcode, and so let's go to Xcode. And our program begins. I'm not going to show the main first. I'll show the main a little bit later. But this is our function getRoots. Same prototype that I showed you earlier. So A is the coefficient of x squared, B is the coefficient of x, and C is the constant. So we compute the discriminant first, which is b squared minus 4ac. And if the zoom is a little less, I can show that to you through this magnifier. So this is my tuple function returning a tuple. So on line 204, I am computing the discriminant, and the quality of quadratic equations is that if this discriminant can have 3 values, if this is 0, then you have just one root, which is minus b divided by 2a. If this is greater than 0, if discriminant is greater than 0, then you have 2 real roots, and if discriminant is negative, then you have 2 imaginary roots. So basically, with respect to these double, double, and double, we declare 3 double types here. Real root 1 set to 0, real root 2 set to 0, and imaginary root, imag root, set that to 0 also. And we set bool is real to true. Okay, so as I said, there are 3 possibilities. Discriminant could be 0, greater than 0, or less than 0. So we are using that in 3 different ways. I have first here, if discriminant is greater than 0, then it has 2 real roots. Okay. Otherwise, okay, actually discriminant is greater than 0 or equal to 0. So we are actually doing both cases here. We could do a separate case if it's 0 or greater than 0, but actually it's perfectly okay to combine them together. Otherwise, discriminant is negative, and so this piece of code here does the negative roots. Sorry, the imaginary roots. Okay, so let's take a look at when discriminant is greater than 0. So obviously, solution in that case is that my real root will be minus b divided by 2a plus sqrt function of discriminant, which we determined over here, b squared minus 4ac, divided by 2a. Okay, so whole thing divided by 2a, or individual divided by 2a. So that's one of the root, and the second root is again minus b divided by 2a minus sqrt of discriminant divided by 2a. So these are our 2 real roots, and actually when discriminant is 0, in that case this part, this second portion here will become actually 0. Okay, and you'll have only minus b divided by 2a. So 2 roots will have same value in that case. Okay. If discriminant is neither greater than 0 nor equal to 0, then it's got to be less than 0. Then we have the imaginary part. So in that case, we set the is real to false. And in that case, 2 real roots will be minus b divided by 2a, and they're actually same in that case. The real part of the square root will be same in this case. But since discriminant is negative, I cannot take square root of a negative number. I actually multiply that by minus 1.0 to make it positive, and then take the square root and then divide by 2a. So this is the imaginary part of my square root. So in that case also I populate all three actually, although first two are the same actually. Okay. And then I use the make tuple function to return the tuple is real, real root 1, real root 2, and imag root. So just understand that is real will be true. It was set to true here and not changed in this if discriminant greater than 0 part. Real root 1 and 2 will be different when I actually have two real roots, when discriminant is actually greater than 0, and in that case imaginary root will be set to 0. And when we have imaginary root, then this will be false, which was set right there, and real root 1 and real root 2 will be same value, and imaginary root will be same also, except in one case the minus will be used and other case plus will be used. Okay, so that's the whole thing, and then my make tuple function returns the tuple. Okay, so this is the case for function. Now I'm going to show you in the main basically how we use the function. So in the main I have a loop, but I'm not going to worry about the loop too much. I'm just going to show you how the function works like one time. Okay, and I've set the set precision, scientific, and show point. I put the output to be scientific rather than fixed, and set precision to 4, and I suppose I can show it to magnified right there. And there's some basic information here that is printed when the program is done. And basically I've done a situation that I declare 3 variables here and set them to A, B, and C. I ask for the leading coefficient A. Person enters the A. Notice there's nothing preventing them by entering A equal to 0. And if they enter A equal to 0, then I don't have a quadratic equation. Then I really have a simple equation, which is Bx plus C. So I tell them that you are entering data for the ordinary equation and not the quadratic equation. And then I ask them to enter coefficient of X or B and constant C. And then solution in that case is very simple. Minus C divided by B will be the solution, and I print them. But I hope that they didn't enter A equal to 0. In that case, my else block executes, and then I ask them coefficient of X, which is B, and coefficient of C, sorry, the constant C. Okay, and really the tuple function getRoots does the whole job. I really don't have to do anything because I have the function doing everything for me. So over here I just call the getRoots function, which takes A, B, and C, and I define my tuple here. I call it item. Tuple is item, has this form. And notice that you don't really have to have such a complicated system. You can just use the keyword auto here, and that will take care of it. Really, this is a simpler way to do it actually, what I just did. In fact, it will still compile and run. Build succeeded. Okay, so what I had earlier was a bit more complicated. In fact, all you need to do is, to make the function call, to call the getRoots, is really set the auto item. So now item is my tuple returned by the function getRoots, which took A, B, and C as an argument. And we already showed you how A, B, and C are used. Okay. All right. Then what I do is, if you remember, the first item was true or false, the Boolean. So get function is used here, and zeroth member is gotten from the tuple call item, and that could be true or false. If it is true, then I have one or two real solutions. So I say if is real, which means if this is true, the solution provided two real roots which are given below, and then we have x1. So we get the item 1 and item 2 using the get function of the tuple, and we print those. Two real roots. If discriminant 0, then x1 and x2 will be same actually, but we just get the item 1, index 1 and index 2 from the tuple. But on the other hand, if is real is false, then else block will execute, and in that case we print the solution produced two imaginary roots which are given below, and then we get item 1 and 2 for the two real parts for the two solutions, and item 3 will be same, except in one case we'll be having plus, another case will be having minus, and we're gonna show again magnified view of that. So x1 will be item 1, item with index 1, which is second item actually, the real part of the root, this is the real part of the imaginary solution, plus the item with sequence 4 or index 4. Yeah, from the tuple item. And notice that we asterisk and I is the square root of -1, which is placed with the imaginary part of the number. So we print the first root, imaginary root, and then we print the second imaginary root here. Only difference between the two roots really will be, in one case the imaginary number will be positive, in other case imaginary number will be negative. Okay. And then of course I have a loop here. If they want to do more, they can do that, and so on. Okay, so I have done this number of values we have entered. I'm going to show you. So I entered A equal to 2, B equal to -5, and C equal to -4, and in that case two real roots were produced. And in a minute I'll 2 -4 -5 -4, I'll run the program for you and show you. But the two real roots in that case was x1 was 3.13 and -6.37. Okay. I think I did something, edit undo. Yeah. Okay, so second was 0.637 minus. And we can run the program with those values, 2 -5 -4. So let's do that here. Okay. 2 -5 -4. And you will get exactly what I showed you earlier, 3.1375 and -6.37 into 10 power -1. If you're not convinced, just go to Wolfram Alpha, type the quadratic equation, and it'll give you the same result that I have here. Okay? Well, I'm just kidding. It should make sense. So if I want to do another one, I enter 0, and it'll ask me again for coefficients A, B, and C. And this time I want to do the imaginary case. And imaginary case, I've entered 5 for A, 4 for B, and 8 for C. So I'll enter those values, 5, 4, and 8, and I get these numbers. X1 is minus 4 into 10 power minus 1, so 0.4, so to speak, and plus and minus 1.2. And let's see what we get. And for 5, 4, and 8, can you see here? I get the same result. Okay. So our getRoot function using tuples work. Okay. And I will put this source code into my blog, and I will provide a link to that also in the video so that you'll have it for the entire source code. This was, by the way, run in the Xcode. It is, hopefully it will run in Visual Studio 2012. But as I have said before, Visual Studio 2012 is not fully compliant with C++ 12. Xcode 5.0 that we are using here may not be fully compliant either, but it is a lot more than Visual Studio. So that's why for doing C++ 11, very often we use the Xcode. Okay. At times we'll use GCC also, because that's GCC 4.8 that I use every now and then for complete compliance with C++ 11. That is fully compliant actually. Okay, so this ends our program, our video on C++ 11 tuple functions. End of the tutorial 2, and thank you so much for watching. Have a good day.